My name is Sumit. I work for Goldman Sachs. I'm here with my colleagues Sumit and Pramod. So for last 1 year, we were working on a solution, search solution for 2 of our applications. We thought we'll show you how we use text search engine or information retrieval system within our system. So the thing is that the problem statement, so what we have done is we have structured this presentation as a case study. So we will talk about 2 different business problems and show you how we use search technology to solve those business problems. The problem statement, of course, is from financial domain, but it's kind of common across enterprises these days. If you look at enterprises these days, they are divided into multiple silos. They have data which is very different. And if we want to build intelligent systems, we need to connect this data across these different silos. And we are hampered these days, or you might have seen a trend that more and more of this data which we are consuming or generating within our systems is unstructured or textual in nature. So let's dive into the problem. So before we dive into the problem, what I'm going to do is first few slides I'm going to cover what financial industry means, what are different businesses we operate in, and what are kind of challenges we try to solve here. The reason behind is that once we take you through a business problem, you will be able to appreciate it more if you understand the domain. So if you look at a bank these days, banks have multiple diverse businesses in which we operate in. On the top what you see is investment banking, where we deal with IPOs, mergers and acquisitions. Below that what you see is investment management. Here we manage clients' funds, pension funds, hedge funds, or really rich guys. Third one is securities. Here we use our own money to invest in bonds, futures, commodities. And the fourth one is research. Here we publish research reports. Some of you might have heard of a term called BRICS. It was coined as one of our research reports. Now why I'm telling you all this is that, as you can see, we make money using very different businesses. So there could be conflict of interest there. And we will cover more in detail as to what I mean by that. So let's look at the challenges which we face. So in this slide what we have done is that I'm going to cover challenges in form of news clippings to show you how things can go wrong in a bank. So let's look at the first news clipping. This is a very recent news clipping. UBS lost $2 billion just because of one rogue trader. It was actually a failure of systems and policies within the bank that they couldn't catch this trader. Let's look at the second one. The second one is very different. It's not an insider. It's not an internal employee which is doing harm to a bank. It's a client. In this case what happened was Mexico's drug traffickers actually used Wachovio's bank account to launder billions of dollars across many years. So if you see this, right, I mean, they obviously had to pay $100 million of fine, but more than that, there was a huge reputational loss, which is very difficult for a bank to recover from. Let's look at the third example here. This example talks about conflict of interest. Here we are talking about conflict of interest between investment bank and research. So SEC actually fined top investment banks approximately $1 billion of fine. And the reason for doing that was that the research department was actually fueling stock price increase, which was being used by investment bank to profit. So here you see a classic example what conflicts can arise within a bank. And these are just simple examples. There are many more ways in which things can go wrong in a bank. There's just few more of that. So now the next question is that if these things go wrong in a bank, what do banks do to prevent those things? So every bank will have a group called compliance. It's just not our bank, every bank has a group called compliance. We call them custodian of our reputation. So what they do is basically, as a bank, they try to prevent such incidents from happening. The way they do that is they look across all these different businesses. They look at data like trading data, they look at deals, they look at the money transfers which are happening, they look at the email, and then try to figure out if there is anything questionable or suspicious. We do an internal investigation after that, and if we find that it requires attention from regulators, we pass that information to regulators for further. So this is what we do. The next question obviously arises that you have a group which does that. Why are these incidents still happening? Why are these incidents still happening so frequently? So let's look at this. Has multiple systems on applications looking across data silos, different businesses. So the first challenge which arises because of that is that all these businesses are very different in nature. Their data is very different in structure and content. So that's the first challenge. The second challenge is that when you look at these incidents which are happening across these different silos, they might not be significant. The moment you start connecting these incidents across the different business silos, you start to build relationships, and that's where you find out patterns. And that's the second challenge. How do we find out these relationships? How do we find out these relationships across these different data sets which we have? The third one is that more and more, as I told you first, like more and more of this data is unstructured. The email contents, there's documents. So more of this data which we are generating is unstructured. So how do we find out? And the key to the relationships is usually hidden in this unstructured data. So I've been talking about unstructured, structured, and semi-structured. Let's look at what they mean actually. Structured is database. Think about database, right? Table, columns. What you see on the right-hand side is unstructured data, which is nothing but textual content which you have in documents or email or so. Semi-structured data is, think of as an XML, right? Where parts of it is like attributes, like what you can see, product ID and so on. But part of it could be raw text. As you can see in a client instruction, here a client has given an instruction that you need to only do a trade only after some hours of so and so on. So this is a textual data. So you can have a combination of structured and unstructured mixed together. And our challenge is that we need to find out attributes as well as this data from it. So now you have some understanding of what our challenges are. So let's dive into the case study. Let's look at those two business problems which we are talking about and what did we do about that. So the two applications we're going to be talking about here are incident management, which manages these incidents, right? I just talked about incidents which happen, money laundering and so on and so on. So the other one is conflicts. The conflict management is slightly different. These two applications are actually very different. One is managing incidents, the other is managing conflicts which arises across these different businesses. And how do we capture that and how do we resolve those conflicts? Now, the theme or the common problem here is still the same. In both these incidents, we would like to find out these relationships which exist. We want to find out if something is going wrong beforehand, even before it becomes public. And the way we want to do is that we want to find out these patterns inside our data. But the challenges which we faced in both these applications are vastly different. And when we look at these applications in detail, we will understand what those challenges were. Let's look at the first application. So, okay, I've been talking about incidents. Let me just give you some examples of incidents, what I mean by incidents. So this application which we talk here about is incident management, which is used by users to do investigation of managing and as well as investigation of those incidents. What you see on the extreme left-hand side where I say incident, well, it's a money laundering. Here, we have found a questionable transaction where a client was actually passing on huge amount of money to an offshore location, and our suspicion was that he is doing for tax evasion. What you see in the center is an incident about email, and here the suspicion is that we found a certain text in his email content which suggested that he is passing on insider information to our client, which is related to some entities. So this is the kind of, there's this very small subset of incidents which can happen, a lot more than that. So the user, when he's using this application and when he sees an incoming incident, when a new incident comes in, what the user wants to do here is that he wants to find out if there are any other incidents in the system, current or historic, which are related to it. And the way we find out relations, way we used to find out related was we used to look at the incoming incident's attributes, and then, like in this case, the incoming incident it's an email incident, it has a client Ted, and he has probably transferred money to a location called Mauritius. So what we used to do it, look at these attributes like Ted, Mauritius, find out if there are any other incidents which are related to it, and use a very attribute-driven search, and then we used to be able to reveal such. It definitely used to reveal certain information, but that was partial. We were missing out on a lot of other incidents which were not revealed by our system. So what we did was we went from attribute-driven search to unstructured data search. When I went from attribute-driven search to unstructured data search, we actually had a combination of both. And suddenly our system started to reveal a lot more information. As you can see on the right-hand side, now this particular incident is not just related to one, it's related to actually 4. And now it's related to 4 because of the fact we were able to search over the user comments, which are users entering the email data or the client instructions, any sort of unstructured data. And what we saw was it started to reveal a story behind this. And the story in this case was like a trader is actually helping a client to pass on insider information. Client is actually making money, and he's also doing tax evasion by passing on to the offshore location. These were kind of patterns which were missing before we didn't have this unstructured data search, and this could only reveal once we implemented that. So the challenge here was, I think, the fact that the data was unstructured. That was our first challenge. The second challenge was it was huge volumes of that data. So let's look at the second application. The second application deals with conflicts. Now this is a very different system. What happens in a bank is that we are working on deals all the time, right? So if you look at the example here, right, the deal PI is basically a private investment. Our private investment division has gone ahead and put our money in some company, in this case, a General Motors Group, while our investment banking division might also be working on an IPO for General Motors Corp. So these are sort of deals which are happening every day, and this particular application sources all these deals across the bank. And what we want to do is that when incoming, so let's say a new deal comes in, what we want to do is that we want to figure out if there are any other deals which are happening may have happened or are happening, currently happening, which has the same company. And the way we used to do it was pick up the name, company name, and trying to find out if there are any other deals, right? And the way we used to do it was kind of an exact match, find out, and we used to get just one particular deal. The problem here, as you can see, that some of your eyes could have easily discerned that if multiple deals which had just some variations of names right there. The problem was these subtle variations of name. The problem here was the data quality. And the data quality issues were there because human errors are bound to happen. The fact that these entities, these companies have multiple child entities where the names could be slightly different. The fact that we also get these names not just from internally, but we are getting from external vendors, which we have absolutely no control over. So when you look at this, what we did was to get over this problem of these subtle variations, we implemented something called fuzzy search. Now, what is fuzzy search? Fuzzy search was just a bundle of multiple different kind of searches together. So we did soundex, spell checks, wildcard, proximity searches, bundle them together so that we can take care of all these name variations. And suddenly we found that our fuzzy search could reveal certain information which was just hidden because our pure database kind of searches wouldn't have revealed this information. So as you look here, right, the problem here is slightly different. The problem here is definitely the data is unstructured because it's a company name. It's also unstructured data. But there is a data quality issue. The data is dirty. So good thing for us was, for both these problems, the solution which we found was one. And for us, the solution was text search engine. Text search engine, if some of you might have already used, it by default comes with the ability to search over text. It gives you all these phrase queries, wildcard, and proximity queries by default. I mean, these look very easy to do that, but when you're searching on millions of documents, actually sometimes could, and your index size could actually go to like few hundred gigabytes. It actually becomes very slow. So they actually implement all these very fast. And the other thing which is supported by most of these text search engines is a ranking mechanism which can rank these search results by relevancy. I mean, as you might have seen when you do a Google search, the first page which comes is very relevant, right? So all these text search engines come with this relevancy ranking model built into it. What you see here is some of the ranking models which they use. So what I'm going to do here is that hand it over to my colleague Sumit, who's going to take you through exactly how did we use this text search engine and which text search engine did we use.
Thanks, Sunit. So as Sunit mentioned, we're going to see how we have leveraged the text search engine capabilities to solve some of our real-life business cases. The first system that we're going to cover is the conflicts management design. So as Sunit mentioned, that for a compliance officer who wants to look for the conflicts of interest scenarios across different deals, the underlying attribute is to match the company names. And the biggest challenge in matching these names is that these names can have variations. So I've taken an example of a company name like Ford Motor & Co. So what we do first is we just pick this name and run it through something what we call as Permutation Generator. It basically generates different alternate variations of the same name. So the first variation is the standardized version, which just strips off any non-alphanumeric characters or non-ASCII characters and standardizes the name. So it becomes Ford Motor with the ampersand replaced by and the trailing dot being removed. The second block, which is the strip name version, it basically strips off any commonly occurring abbreviations in the company names like Co or Incorporated. So what you see is what remains is just the Ford Motor. And the third one, which is the expanded name, it just replaces these abbreviations with the corresponding full text. So the Co is replaced by company and you get Ford Motor and Company. Now once these variations are generated, we then index them into text search engine. Now as Sunit mentioned, that the key behind matching these names is using the fuzzy search. And fuzzy search is a bundle of different search paradigms. So we zeroed in on 3 of these paradigms which actually work very well for company names. The first one being the wildcard matching, like the begins, the contains matches, and the sounds like matching, the phonetic matches, and the spell checks. So for implementing each of these search paradigms, the text search engine gives you some out-of-the-box components. So right on the top, you see the n-gram analyzer. It basically picks up the individual words from the company names and split them into tokens so that you can perform wildcards. So you can see the Ford will get split into FOR, ORD, and FORD. So if you type any of these tokens, you are straight going to get a match on this. The phonetic filter factory just picks up these words and then adds the soundex codes for each one of them before indexing so that you can perform a sounds-like match. And the simplest of all is the text tokenizer, which just picks up the company names and then splits them by white space character and indexes the individual tokens. And then you can perform your spell check against each of these individual tokens using a string matching algorithm like Levenstein or the edit distance algorithms. Now let's see the query side. What happens when the compliance officer comes in and he's actually looking for the deals matching a name, say for example, Ford Motor UK Holdings Limited. The first thing that we need to do is to ensure that it goes through the same set of steps that we went through while indexing so that there is an accurate string matching happening. So we run it through the standardization and stripping of the commonly occurring words process, and what you get at the end is Ford Motor UK Holdings. Now, important point to note here is that if we just do a simple, say, OR between each of these individual tokens and fire a query like Ford or Motor or UK or Holdings, you're going to get tons of results because a word like Motor or Holdings can occur in so many company names. So we built a bit of an intelligence out here. What we did was we did the statistical analysis of company names from different data sources and ascertained that it's only the first 40% of the tokens which actually give a unique identity to a company name, and the remaining 60% are less significant. So what we do in our query, we always do an AND between the first 40% tokens and an OR between the trailing 60% and get a relatively balanced result set. Moving on to the next system that Sumit talked about, the incident management system, where you have incidents getting reported from different business silos. Now the biggest challenge here, if you remember, was searching across the unstructured data formats. So what we see on the left-hand side, these are the formats in which data can come from different silos. So it could be a structured XML with well-defined attributes like trader is Smith and the product is IBM and the client is, say, Mary. Or it could be semi-structured where a user comment is added which is just pure text and the name Ted is embedded inside the text. Or it could be purely unstructured where the incidents have been reported in the form of email with attachments like PDF files and doc files. So what we do is we just pick up the data coming in these different formats and then index them into search engine. You can see different components available which analyze the incoming text. The first one being the XML tokenizer, which just strips off the XML tags and parses out the attribute. We have built in a bit of an intelligence here that the XML tokenizer is now also able to recognize the XML definitions coming from different silos which may have entirely different schemas, and still being able to derive the right context out of it that, okay, what's my trader Smith in this XML vis-a-vis the other one. The text tokenizer, as we saw before, it just splits the text by white space characters, and text extractor is basically responsible for parsing through these documents like PDFs and the doc files and extracting the English text as well as any sort of metadata like author or version number or the date of the document. Now, once the data is indexed and the unstructured data is now searchable, on the search side, when the user comes in, he wants to look for, say, an incident on trader Smith and the product IBM. Now, what we need to do first is to convert the simple user query into a query that follows the semantics of the search engine. So we do two things. We want to ensure that we are searching across all the possible different unstructured data sources. So we do an OR between the XML and the user comments. And plus, we also do an OR between the individual tokens, the trader Smith and the product IBM, so that we ensure that we get as many incidents as possible from the search engine. But once we do that, there's another challenge. How do you make sure that your compliance officer who is looking at these tons of incidents is able to drill down into those incidents and able to identify those suspicious scenarios? So for that, we give the faceting or the filtering functionality which just group buys these results by different attributes, say product or trader by incident names. So user can directly drill down into those individual group sets. And also in compliance, always you need to make sure that the compliance officer is only looking at incidents to which he has entitlements. And for that, we add additional filters to the search query which enforces those entitlements. Now we have been talking about the text search engine in all our slides. So I want to break that suspense at what text search engine we are using. We are using Apache SOLR. It's an open source project. And the reason we are using are several. The top one being that it provides you a RESTful API over Apache Lucene. Apache Lucene is a very popular open source Java project for text indexing and searching. And with a RESTful API, the biggest advantage you get is that you can build your GUI in any sort of technology you want, like PHP or JSP, and still you are in a situation to query your search engine and get the desired results. It's a very popular open source project with good developer support and a lot of detailed documentation available on web. And it has an extensible architecture, gives a lot of freedom to developers to develop their own components and plug it in, which we'll see shortly. It's very fast and scalable, can consume huge volumes of data. Index is very fast and then supports blazing fast search capabilities over them. It has a small but a cool feature called the web administration interface, which is very helpful for developers during the development phase for tuning up their Solar instances, and also during the production phase for doing any kind of performance monitoring. And yes, it's also used by other corporations like AOL, CNET, and eBay, and they're using it under very high performance environments. So now once we know what search engine we are using, let's take a detailed look at the architecture of Solar. I mentioned that the Solar has a RESTful API, so you can query that Solar engine over HTTP protocol. Now I'm going to take you through that journey, that how an HTTP query comes in and it hits your search engine.
With a client API known as SOLR-J, which can convert this XML document into Java objects. Once we have those Java objects, we need to convert it back into our application-specific objects. Once we have that, you render those back onto the UI. So that's it on the query side. Now coming to the indexing architecture. Now on the index side, what we had was like we had multiple sources of data. We have different silos sending us these messages. We have feed files coming directly into database. At the same time, we have users who are actually viewing this incidents on the UI and actually either giving some comments, attaching documents to them. So what we needed to do is we needed to index these at near real time. So what we did was we maintained a database queue which actually captures this incoming events. Now there are few reasons why we went for a database queue. First thing is we wanted to make sure that the incidents that are coming in are indexed in the same order as they are coming in. So because what happens is, let's say suppose an incident comes in and user attaches a document to that. If we try to index the document first before the incident in the index, your index will fail, right? Because it doesn't have the incident itself. So that's one. Second is Solar doesn't provide us XA transaction capabilities. So how do we do that? So to provide XA transaction capabilities, we put this queue into our database. So now what we can do is, if there is a failure on the application side, we can actually roll back the application data as well as the queue itself. Or if there is a failure on the server side, application is not impacted. It will just keep on adding new incidents into the queue. Now we have a component called Search Engine Updater, which is actually constantly polling this database queue. Once there is a new incident, it creates a total document, again using SOLR-J APIs, and indexes it into the Solar. Now important thing again out here is, when you add a document to the Solar index, it is not immediately searchable. You have to fire another command called commit. When you fire a commit, the index data is actually written down into the disk. So naturally commit is a much more costlier operation. So what you need to do is you need to add a bunch of documents and then only call the commit command. Again, Solar comes with auto commit. So you can configure saying that, okay, commit after every minute or commit after every 10,000 documents. But we have built in our own custom logic to when and where to fire commit. Okay, on the Solar server side, what happens is all the updates that are coming in are actually captured by the Solar master Solar server, which is responsible for indexing the data. And we have a whole set of slaves that are actually servicing the client request. What these slaves do is they actually pull data from master server using HTTP pull. On the extreme right side, we have a bulk indexer. What bulk indexer does is it pulls out, so when you are setting up your application for the first time, right, you need some way to index all the data. So that's where bulk indexer comes in. Solar again comes with its own bulk indexer. They call it import handlers. What they can do is they can actually poll your database tables constantly, and if there is a new event, read it and index it. Moving on to the next slide. Yeah. Yes. So again, if your master goes down, so what will happen is the events will again be queued up in your queue, right? So if something goes down, your application is not impacted. Capability of search definitely is impacted, but once the server comes back up, you can replay the messages. Okay. So these are some of the new features that are coming into the Solar Cloud. So again, built as we see, right? Master server probably not enough. We need a cloud for higher availability, tolerance, and internally it will again use another Apache project, Zookeeper, for configuration and coordination. Pseudo join. Again, Solar is a flat schema, right? So how do you join between, so there's no concept of join. But in the newer version of Solar, what you can do is you can actually join between two different schemas of Solar. So you can fire a query which actually searches a result on one schema and joins back the result with another schema. Field collapsing. So let's take an example. Let's say you go to a web store, right, and searches for Hyundai Santro car. So on the index side, there will be tons of documents for Hyundai Santro, which just differs by color. So you'll have a red Santro, you will have a green Santro. But when you are displaying the result back to the user, you want to show that, okay, there's only one Santro, which are variations in color. So the field collapsing does exactly that. So you have to say that, okay, I want to collapse my results based on color attribute. So, and it will return you the documents and tell you what are the variations in color are. Pivot faceting is nothing but hierarchical faceting. So till now you can just say, okay, I want to facet by color, right? Now you can say that, okay, I want to facet by color and car type. So what kind of questions can you answer using pivot faceting? Now you can say that, okay, I want to find all the sedans that are manufactured by Maruti. So you are faceting actually on two different dimensions. One is the manufacturer and another one is the car type. Finally is functional queries. So important aspect of any text search engine is ranking, right? How do you rank? So even though Solar has a very good ranking system, it may not be applicable in all situations, right? So now they give you an ability to fit in your custom algorithms to rank your documents. So, okay, next slide. Okay, so just to recap, what we have seen in today's presentation is today's enterprise application just does not contain structured data. They contain semi-structured and unstructured data. What we have seen that is text search engine provide us the ability to search all these three types of data with a single interface. And what we have seen is if we are doing only relational search or only structured search, then we are definitely going to miss on some important facts. With that, we conclude our presentation and we are open for questions.